is stress times strain. And if you want to be a little bit more rigorous, and we're going to do that later on, if this is sigma, if this is epsilon, and I'm loading this with a linear relationship between stress and strain, the area underneath that, that's going to be dW, right? And that's going to be equal to stress times the variation of strain. And so this is going to be, and because it's going to be underneath that line, is going to be 1/2 of sigma times dE. But we know that sigma is K times strain, right? Where K is the bulk modulus. So you can also write this as the square of that. So just to be clear, it's all of this. Okay, don't worry about this equation right now. Let's just work through this equation. What else can I do to add energy to that solid? What other kind of strain I can add to that? There is something I have neglected so far. But, I mean, if we're talking in poromechanics and continuum mechanics, we need to include it. This is a volumetric strain. I could also add shear strains, right? So I could have also energy in which, since this is a solid, I could add a shear strain, and that additional component is going to be equal to the tensor of the deviatoric stresses times the tensor of the deviatoric strains. Don't worry too much about this, okay? You will see that later. We do not need to go in detail about solving this one, because this is the same as with any solid. Pressure is not going to add any energy in the shear part. So this is deviatoric stress tensor. This is a infinitesimal variation of the deviatoric strain tensor. We didn't calculate what was the deviatoric strain tensor, but it's the same as with deviatoric stress tensor. You just subtract the volumetric part of the tensor, and what is left is the deviatoric strain. Well, this will be the case of a solid with no pores. In a solid with pores, we're going to have, let me move this one, leave it up so I have space. Very similar to the one before, we're going to have a component which is volumetric, and let me just, that's going to be a pore, okay, just one pore, just to make it simple. We're going to have a component which is going to be shear, and we're going to have another component which is the energy stored in the solid by deforming the porosity. So all of that together is going to end up in an equation for the porous solid, which is going to look like this. Change of porosity. So I could notice that this one is equal to that one, okay? So with this equation, and considering the total energy now that we have, and considering the part of pressure, we can write a more general equation that allows us, in the same way that we wrote this equation over here, to write an equation for the total energy of the porous solid, of just of the solid part. But we'll get into that on Tuesday, because that's going to require a lot of our attention. Okay? All right, guys. See you next week. Have a good weekend.
Thank you, too.
Thank you.
Homework due on Monday.
Monday, yeah, I'm going to change that today.
Midnight, like you mean?
What?